On the 1st of July 2026, the United States Geological Survey published its monthly update on the Yellowstone volcanic system, and buried inside a routine government report was a number worth sitting with. During June alone, monitoring stations across the region located 118 earthquakes beneath Yellowstone National Park. The largest of them, a microearthquake of magnitude 2.4, struck about 12 miles south-southeast of Yellowstone Lake on the 7th of June, just before 6 in the morning. 2 weeks later, at just after 5 in the morning on June 13th, the ground near Black Diamond Pool and Biscuit Basin let go, throwing rocks tens of feet into the air in a small hydrothermal explosion that was picked up instantly by seismic and acoustic sensors. None of this made the volcano more dangerous. The alert level that day, and every day this year, has remained at normal, the lowest of 4 tiers the USGS uses, with the aviation color code sitting at green. And yet, something about how scientists are watching Yellowstone right now really has shifted, and it is worth understanding exactly what that shift is, because it is not the shift most people assume. For decades, the story of Yellowstone has followed a familiar script. A journalist notices a swarm of small earthquakes, or a geyser behaves strangely, or a stretch of ground rises by a few millimeters, and within days, the story has mutated into speculation about an overdue super eruption capable of burying half a continent in ash. That narrative has deep roots. It was seeded by television documentaries decades ago and has been repeated so often that it now functions almost like folklore. A story people believe because they have heard it so many times, not because the evidence supports it. What is actually happening beneath Yellowstone right now is a different kind of story, and honestly, a more interesting one. It is not a story about a volcano waking up. It is a story about science catching up to a volcano that has been doing more or less the same things for hundreds of thousands of years. Except now, for the first time, researchers have the tools to actually see it clearly. 3 separate strands of research have converged in the past 12 months, and each one on its own would have been a notable development. Together, they represent something closer to a genuine leap in understanding. The first strand involves artificial intelligence quietly rewriting the seismic history of the park. The second involves a redrawing of the deep plumbing system that feeds Yellowstone with heat, a model that challenges an idea that has stood largely unchallenged since the 1990s. The third involves a much sharper, closer look at where the magma itself actually sits beneath the surface, using techniques that did not exist even 5 years ago. None of these 3 findings, taken individually or together, suggests an eruption is approaching, but all 3 suggest that scientists have been working for a very long time with an incomplete picture. That incompleteness is now being corrected piece by piece, and the corrected picture is more detailed and more dynamic than the one people have been picturing since childhood. Before going further, it is worth pausing on what the word supervolcano actually means in scientific terms, because the term itself does a lot of unearned work in generating fear. Volcanologists classify eruptions using something called the Volcanic Explosivity Index, a scale that runs from 0 up to 8, with each step representing roughly a 10-fold increase in the volume of material ejected. A supervolcano, in the technical sense, is simply a volcanic system capable of producing an eruption that reaches level 8 on that scale, ejecting more than 1,000 cubic kilometers of material in a single event. Yellowstone has done this 3 times in its known history, which is precisely why it carries the label. But the label describes a capability demonstrated in the deep past, not a status the system carries every single day like a loaded weapon. Comparing Yellowstone's current state to its capability during a super eruption is a little like calling a resting marathon runner dangerous because of what their body is theoretically capable of doing during a race. The capability exists in the geological record. The active conditions required to trigger it do not currently exist in the data. It also helps to understand that Yellowstone did not simply appear beneath Wyoming out of nowhere. The volcanic activity now centered on the park is the most recent expression of a much older hotspot track that stretches roughly southwest to northeast across the Snake River Plain, through southern Idaho, and into northwestern Wyoming. Over the course of roughly 17 million years, this hotspot has produced a chain of calderas, each one active for a period before the tectonic plate above it drifted onward, and a new caldera began forming further along the track. Yellowstone represents simply the current, most recent position in that long geological march. The older calderas along the Snake River Plain are now extinct, cooled, and geologically quiet, which is itself a useful reminder that these systems do not stay violently active forever. They pass through phases, and the caldera sitting beneath the park today is, geologically speaking, still a young and active member of that long lineage. Start with the earthquakes, because they are the most visible and most talked about signal to come out of Yellowstone in any given year. The park sits atop one of the most seismically active regions in the country, and it produces somewhere between 1,500 and 2,500 recorded earthquakes annually. The overwhelming majority of these are too small to be felt by anyone standing directly above them. They are picked up only because Yellowstone carries one of the densest seismic monitoring networks on the planet, a web of instruments capable of detecting motion measured in fractions of a millimeter. For years, the way scientists built their earthquake catalog was fundamentally a manual process. Trained analysts sat with recordings and combed through the data by eye, identifying the telltale signatures of an earthquake against a background of noise. It worked, but it had an obvious limitation. The smallest events, the ones sitting right at the edge of what the instruments could register, often slipped through simply because no human being can review 15 years of continuous data with perfect consistency. That changed in the summer of 2025. A team led by an engineering researcher at Western University, working alongside collaborators in Colombia and scientists at the U.S. Geological Survey, took 15 years of raw seismic recordings from Yellowstone and ran them through a machine learning system built specifically to hunt for the seismic fingerprints that human reviewers tend to miss. The results, published in the journal Science Advances in July of that year, were startling in scale. The algorithm did not just catch a few earthquakes that had been overlooked. It identified roughly 10 times more seismic events than had previously been logged for that same period, pulling tens of thousands of additional earthquakes out of data that had already been examined by trained professionals. This was not evidence of a volcano suddenly becoming more active. It was evidence that Yellowstone had always been this seismically busy, and that the tools available before simply were not sensitive enough to register the full picture. What the researchers found buried in that expanded catalog turned out to be just as interesting as the raw numbers. More than half of all the earthquakes at Yellowstone cluster into what scientists call swarms, tight-knit families of small quakes that occur close together in space and time and often appear to migrate, shifting gradually along a path over the course of hours, days, or weeks. Swarms are not unusual for Yellowstone. They are, in fact, one of its defining seismic characteristics, distinguishing it from regions where earthquakes tend to occur as isolated, unconnected events. What makes swarms scientifically valuable is that their movement traces something happening underground. When a swarm migrates along a particular path, it is very often tracking the movement of fluid or gas through cracks and fractures in the crust, or the redistribution of stress along a fault system. Being able to see that migration in much finer detail, thanks to a data set 10 times richer than before, gives researchers a genuinely improved ability to distinguish between the routine background hum of a hydrothermal system doing what it always does and something that might actually represent a meaningful change in behavior. The study's authors were careful to underline exactly this point. A bigger earthquake catalog is not the same thing as a more dangerous volcano. Nearly all of the newly discovered events were smaller than magnitude 1.5, well below the threshold most people would ever notice, let alone worry about. The second major thread in this story concerns not the earthquakes themselves, but the ground they occur on, and the slow vertical dance that the Yellowstone caldera performs year after year, almost like breathing. Scattered across the region are dozens of continuous GPS stations, instruments precise enough to detect ground movement on the scale of millimeters. What they show when you look at the long-term record is a system in constant, gentle motion. The caldera floor rises and falls, typically by around an inch or 2 to 3 centimeters in a given year. Since 2015, the general trend has actually been downward, with the caldera slowly subsiding at roughly that same modest rate. This kind of movement, up in some years, down in others, is considered entirely normal and has been documented for decades. It reflects the underlying volcanic and hydrothermal system doing what such systems do: fluids moving, pressure redistributing, heat shifting beneath the crust. In July of 2025, something slightly more specific caught the attention of researchers. A stretch of ground along the northern rim of the caldera began to lift. This was not unprecedented territory. The same general area had experienced similar uplift episodes in 1996 and again in 2004, incidents that came to be known collectively as the Norris Uplift Anomaly, named for its proximity to the Norris Geyser Basin. Those earlier episodes prompted genuine scientific curiosity at the time about whether the uplift might foreshadow increased seismic activity, larger earthquakes, or shallow buildup of hydrothermal fluid pressure close to the surface. This newest episode was watched with the same kind of professional attention. And then, by the middle of January 2026, it simply stopped. Since that point, according to continuous monitoring data, there has been no significant further uplift and no significant subsidence recorded along that stretch of the caldera rim. The ground rose, paused, and settled back into its familiar rhythm, the same way it has after previous uplift episodes going back decades. Nothing about the event, in isolation or in the context of what came before it, suggested it was building toward anything more dramatic. It was simply the caldera doing what calderas like Yellowstone periodically do. The third and arguably most conceptually significant development landed in April of 2026, when a research team based at the Institute of Geology and Geophysics at the Chinese Academy of Sciences published a paper in the journal Science that proposed something close to a fundamental revision of how Yellowstone actually works. For roughly 3 decades, the dominant explanation for Yellowstone's extraordinary heat has centered on the idea of a deep mantle plume, a column of superheated material believed to rise almost vertically from somewhere near the boundary between Earth's core and its mantle, punching through the crust like a fixed torch while the North American continent slides slowly over the top of it. It is an elegant idea, and it does explain part of the puzzle, particularly the long chain of extinct calderas stretching across the Snake River Plain that mark where this hotspot supposedly sat in earlier geological epochs. But the plume model always struggled to fully explain certain features of Yellowstone's behavior, including just how much of the region seems to function as a broad, distributed zone of heat rather than a single, narrow conduit. The new research team built a 3-dimensional model of the entire mantle beneath the western half of North America and arrived at a rather different picture. Their analysis suggests that most of the magma feeding Yellowstone does not, in fact, originate from a narrow plume rising from the deep mantle at all. Instead, it appears to come from the shallow asthenosphere, the semi-molten layer of the upper mantle sitting just beneath Earth's rigid outer shell, with comparatively little direct contribution from anything deeper. According to this model, the driving mechanism is tectonic rather than plume-based, as the remnants of an ancient tectonic plate called the Farallon Plate, long since subducted and now sitting deep beneath the central and eastern portions of North America, continue their slow descent. They set up what researchers describe as an eastward mantle wind, a broad sideways flow of hot material dragged along beneath the tectonic plates. That lateral flow, rather than a vertical plume, is what the new model proposes as the actual engine feeding heat toward the Yellowstone region, with the material migrating through a tectonically controlled network and evolving as it collects in reservoirs within the crust. This is not merely an academic reshuffling of terminology. It changes the physical picture of what lies beneath the park in a meaningful way. If the magma supply is being fed sideways through a distributed system controlled by tectonic stretching, rather than punched upward through a single plume, then the underground plumbing is likely to be more tangled, more interconnected, and frankly, more extensive than the simpler plume model implied. As molten material works its way toward the surface under this scenario, it mixes with the surrounding rock and forms a thick, viscous mush, something more like wet sand than the sort of free-flowing liquid rock most people picture when they hear the word magma. That mush moves sluggishly and resists flow, and this detail matters enormously for anyone trying to assess actual eruption risk, because a system dominated by slow, sticky mush is a system that is far less capable of moving quickly toward the surface in the way that would be required to trigger a large eruption. The researchers behind the paper were explicit that their findings do not indicate Yellowstone is approaching any kind of eruptive event. What their model does is offer, for the first time, a physically coherent explanation for why the region above this magma system is so broad, so heat-rich, and so seismically active across such a wide footprint, rather than being concentrated tightly around one narrow point. Running alongside this deep, continental-scale remodeling was a much more localized but equally striking discovery about how close to the surface some of Yellowstone's magma actually sits. In 2025, researchers working with data from geophysicists at Rice University, building on techniques developed with colleagues at the University of Utah and the University of New Mexico, used artificial seismic vibrations, essentially controlled shock waves, sent into the ground and tracked as they bounced back to map the uppermost boundary of the shallow magma reservoir with a level of precision that had not previously been possible. What they found was a sharp, well-defined cap sitting at a depth of roughly 3.8 kilometers, about 2.5 miles beneath the surface. This cap appears to be rich in volatile compounds, meaning gases and fluids trapped within partially molten rock, forming a distinct layer that marks the true top of the shallow magma body underlying the caldera. On its own, a number like 3.8 kilometers can sound alarming. It is, after all, closer to the surface than many people would instinctively guess a supervolcano's magma reservoir to be. But depth by itself tells you very little about danger. What actually determines whether a magma body poses any near-term threat is its physical state, and on that front, the data has remained remarkably consistent for years. According to the U.S. Geological Survey, the magma chamber beneath Yellowstone caldera is only somewhere between 5 and 15% molten at any given time. The remaining 85 to 95% is solid or near-solid crystalline rock, packed together in a configuration that behaves nothing like the free-flowing lava pool that popular imagination, fed by decades of disaster films, tends to conjure. A body of rock that is overwhelmingly solid simply cannot erupt in the way a mostly liquid one could. It would first need to heat up substantially, melt a much larger fraction of itself, and build enough internal pressure to force its way upward. And all of that would take a very long time, generating detectable warning signs at every stage along the way. It helps at this point to put some historical context around what an actual eruption at Yellowstone has looked like, because the historical record itself argues strongly against imminent catastrophe. The most recent volcanic eruption in the Yellowstone region was a lava flow that occurred around 70,000 years ago, a relatively modest event by the standards of the system's deeper history. The last truly cataclysmic supereruption, the kind of event that carved out the caldera visitors walk across today and blanketed a significant portion of the continent in ash, occurred approximately 640,000 years ago. Before that, Yellowstone experienced two earlier major eruptions, one around 2.1 million years ago and another around 1.3 million years ago. Averaged together, those three events are separated by roughly 725,000 years. If you extend that average forward from the most recent supereruption, you land somewhere in the neighborhood of 100,000 years still remaining before another event of similar scale might be expected. It is worth being honest about how shaky that kind of math really is. It is derived from only two intervals between 3 data points, which is a painfully small sample size for any statistical claim. And scientists who study Yellowstone are the first to say that treating it as a genuine prediction is close to meaningless. But even taken as a rough, loose approximation, it does not point toward anything remotely imminent. The USGS has also worked to quantify eruption risk in more formal probabilistic terms, and the numbers they have produced are consistently, almost overwhelmingly, reassuring. Current estimates place the annual probability of any volcanic eruption at Yellowstone, let alone one on the scale of a supereruption, at somewhere around 0.001%, a figure so small that many scientists consider it likely to be an overestimate for the near term rather than an underestimate. To put that kind of probability into perspective, a person is statistically far more likely to be struck by lightning in a given year, or to be involved in a fatal car accident on a short drive, than Yellowstone is to erupt in any way at all during that same period. It is also worth appreciating just how much of Yellowstone's activity is expressed not through earthquakes or ground movement at all, but through its famous hydrothermal features, because these are, in a very real sense, the most visible pressure valve of the entire system. The park sits atop more than 10,000 hydrothermal features, including roughly 500 active geysers, which together represent more than half of all the geysers known to exist anywhere on the planet. Old Faithful, the most photographed of them, erupts with such reliable regularity precisely because the plumbing feeding it has remained stable for a very long time. Norris Geyser Basin, the hottest and most dynamic thermal area in the park, includes Steamboat Geyser, the tallest active geyser in the world, capable of shooting water more than 300 feet into the air during its larger eruptions, though the intervals between those eruptions can vary from days to years depending on the underlying plumbing conditions. Aquinas Geyser, also in the Norris Basin, continued its own pattern of activity through June of 2026 with an eruption recorded that month, a small but telling sign that the basin's underground water and heat system is functioning exactly as it always has. These features exist because shallow groundwater comes into contact with heat rising from below, and the entire network acts as a continuous release mechanism, venting heat and pressure gradually rather than allowing it to accumulate. A hydrothermal system this active, this consistent, and this well-studied is itself a kind of reassurance. It is heat finding its way to the surface through thousands of small, well-understood channels, rather than heat building silently toward a single catastrophic release. The scale of the monitoring effort behind all of this deserves its own mention because it is easy to take for granted just how thoroughly watched this particular patch of Wyoming, Montana, and Idaho actually is. The Yellowstone Volcano Observatory is a formal partnership bringing together the U.S. Geological Survey, the University of Utah, Yellowstone National Park itself, and several other research institutions, all coordinating a monitoring effort that includes seismometers scattered across the region, continuous GPS stations tracking ground movement to within millimeters, satellite-based radar interferometry capable of detecting deformation across the entire caldera from orbit, stream gauges monitoring changes in water chemistry and flow, and temperature sensors placed throughout the park's thermal areas. In July of 2026, scientists began installing yet another layer to this network, a new monitoring station equipped with seismic and infrasound sensors specifically placed in the Upper Geyser Basin, the area surrounding Old Faithful itself, adding still more resolution to a system that was already among the most densely monitored volcanic regions on Earth. This is not a volcano being watched casually or intermittently. It is arguably the most intensively studied volcanic system on the planet, observed continuously by instruments that would catch a meaningful change within hours, not months. None of this means the system is inert, or that scientists have stopped watching closely, because they have not. And this is really where the phrase new phase earns its meaning. What has changed is not Yellowstone's underlying behavior. What has changed is the resolution at which humans can observe that behavior. Consider what a genuine buildup toward a major eruption is actually believed to look like, based on both the geological record and observations of comparable volcanic systems elsewhere in the world. Most volcanologists believe the precursors to a catastrophic eruption at a system like Yellowstone would be detectable well in advance, likely over a period stretching from weeks to months and possibly longer. Those precursors would include intense, sustained earthquake swarms far beyond anything in the current record. Rapid and dramatic ground deformation, measured not in millimeters, but in meters. Dramatic changes in the chemistry and temperature of the region's famous hydrothermal features, and a cascade of other signals that would be, in the words of the scientists who study the system daily, unmistakable. Right now, according to every instrument currently trained on the park, not one of those precursors is present. The earthquakes remain small and consistent with historical background rates, even after accounting for the far larger number now being detected by machine learning. The ground deformation has settled back into its familiar, gentle up and down rhythm. The hydrothermal features, including the geysers that draw millions of visitors every year, continue behaving as they always have, punctuated by occasional small hydrothermal explosions, like the one at Biscuit Basin in June, which are themselves a routine, well-understood phenomenon caused by the sudden flashing of superheated water into steam, not by rising magma. What this convergence of research really represents, then, is an enormous improvement in the fidelity of observation, rather than any meaningful change in the volcano's actual state. Scientists now have a machine learning-generated seismic catalog roughly 10 times more detailed than what existed before, giving them a far more granular view of how stress and fluid move through the crust beneath the park. They have a new continental-scale model of the mantle that offers a more physically coherent explanation for why Yellowstone behaves the way it does, replacing a simplified plume narrative with a richer, tectonically grounded picture of shallow, sideways flowing heat. And they have a precisely mapped shallow magma cap, imaged with techniques that simply did not exist a decade ago, giving researchers a clearer sense of exactly where the boundary between solid crust and partially molten rock actually sits. Each of these advances on its own would represent a meaningful contribution to volcanology. Together, arriving within the same 12-month window, they genuinely do mark the beginning of a new chapter in how this particular volcanic system is understood. There is also something worth saying about why this particular volcano generates so much more public anxiety than other, arguably more immediately dangerous volcanic systems around the world. Part of it is sheer familiarity. Millions of people visit Yellowstone National Park every single year, walking directly across boardwalks that sit above an active hydrothermal system, watching geysers erupt a few dozen feet away, and that intimate physical proximity creates a psychological connection that a distant volcano in a country most people will never visit simply cannot replicate. Part of it is the scale of the imagery associated with worst-case scenarios. Modeling exercises exploring hypothetical super-eruption scenarios have described ashfall reaching across much of the central United States, and volcanic gases potentially cooling global temperatures for years afterward. And those images, once absorbed, tend to stick regardless of how remote the underlying probability actually is. And part of it is simply the media cycle itself. Earthquake swarms are genuinely newsworthy, uplift episodes are genuinely newsworthy, and a new scientific paper is genuinely newsworthy, but each of these stories tends to get covered in isolation, stripped of the broader context that would normally accompany it, and stripped-down stories travel faster and generate more anxiety than fully contextualized ones. A headline describing 97 earthquakes in a month sounds dramatic on its own. The same headline sounds almost boring once you know the region typically produces between 1,500 and 2,500 earthquakes in an average year, and that this particular month fell well within that normal range. This pattern is not unique to Yellowstone. Similar discoveries have recently surfaced elsewhere, including a supervolcanic system identified beneath the Tuscany region of Italy, a reminder that Earth's crust hides more of these dormant giant systems than most people realize, and that improved detection technology is now surfacing them faster than at any point in the history of geology. What distinguishes Yellowstone is simply the density and duration of attention it receives, not the uniqueness of its underlying risk profile. Volcanologists who study these systems professionally tend to describe their relationship with Yellowstone in far calmer terms than the headlines suggest, treating each new earthquake, swarm, or research paper as another data point in a decades-long project of characterization, not as a fire alarm demanding immediate public concern. That is the real story hiding underneath every alarming headline about Yellowstone that has circulated so far in 2026. It is not a story about a supervolcano stirring after millennia of dormancy. Yellowstone has never truly been dormant in the way people sometimes imagine. It has always been earthquake-prone, always been breathing gently up and down, always been venting heat through thousands of hydrothermal features scattered across the park. What is genuinely new is the sharpness of the picture scientists now have of all that ordinary activity and the theoretical framework they can use to make sense of it. There's a particular kind of irony built into that improvement, too. The better the tools become, the more data they generate, and the more data that gets generated, the more raw material exists for alarming headlines to be built from, even when the underlying reality is one of remarkable stability. 10 times more earthquakes than the catalog sounds, at a glance, like 10 times more danger. It is nothing of the sort. It is 10 times more insight into a system that has been behaving essentially the same way for a very long time. If there's a genuine takeaway from everything that has emerged over the past year, it is this. The instruments watching Yellowstone today are more sensitive, more numerous, and more capable of synthesis than at any point in the volcano's monitored history. That matters enormously, not because it suggests danger is closer than previously thought, but because it means that if the system's behavior ever did begin to shift in a genuinely concerning direction, scientists would very likely see it coming with more lead time and more clarity than would have been possible even 5 years ago. The alert level remains at normal. The aviation color code remains at green. The earthquakes remain small. The ground is settled. The magma remains mostly solid, sitting exactly where models have long placed it, just now mapped with sharper precision. Yellowstone is not entering a new phase of activity. It is entering a new phase of being understood. And for a system this vast, this old, and this consequential, should it ever truly awaken, understanding it better is, without question, the outcome anyone living downstream of it should actually want. There is a broader lesson buried in all of this, one that extends well beyond Yellowstone itself. Scientific instruments and analytical methods keep improving, year after year, and every improvement inevitably produces a temporary surge of new data that can look, on first glance, like a surge of new danger. Machine learning finds 10 times more earthquakes, and it feels like the ground has become 10 times more restless. A new mantle model reveals a broader, more interconnected magma system, and it feels like more fuel has somehow been added to a fire. A sharper seismic image locates a magma cap only a few kilometers down, and it feels like the volcano has somehow crept closer to the surface overnight. In every one of these cases, what has actually changed is resolution, not reality. The volcano beneath Yellowstone today is, as far as any instrument can tell, behaving essentially the way it has behaved for tens of thousands of years. Mostly solid, slowly breathing, venting heat through thousands of geysers and hot springs, and shaking gently with small earthquakes that mostly nobody will ever feel. Understanding that distinction between better detection and greater danger is probably the single most useful thing anyone can take away from a year as data-rich as this one has been for Yellowstone research. The scientists spending their careers on this volcano are not bracing for an imminent catastrophe. They are doing what scientists have always done when new tools become available, pointing them at an old, familiar system and discovering, layer by layer, just how much more complex, interconnected, and quietly dynamic that system has been all along, hiding in plain sight beneath the boardwalks, the geysers, and the steady stream of visitors who walk across it every single day without a second thought, which, given everything the data actually shows, remains the entirely rational way to treat it.